Hi, everybody. It's Professor Mitchell. We are wrapping up Chapter 3 with this video on Section 3.4, which is, again, linear programming, kind of a special situation with linear programming. So in particular, in this section, we'll deal with linear programming problems where it looks like you need more than two variables, but you actually don't. And we'll illustrate that with a transportation example. On the surface, some problems may appear to have more than two variables. However, sometimes they can be translated into mathematical language so that only two variables are required. So as an example of that, a TV dealer has stores in city A and B and warehouses in cities W and V. These cities are all in the state of Maryland. The cost of shipping a TV from W to A is $6, from V to A is $3, from W to B is $9, and from V to B is $5. A store in city A orders 25 TV sets, and a store in B orders 30 sets. The W warehouse has a stock of 45 sets, and the warehouse in city V has 40. What is the most economical way to supply the two stores the requested number of TV sets? So the first thing that's very helpful to do in a problem like this is to make a diagram. There was a lot of information flying around there. And maybe just show you for a second why what makes this problem kind of interesting, and the answer is not super obvious. So, for example, the cheapest way to get TV sets to store B is from warehouse W. It's only $3. So you start to think, okay, let's send all 30 TV sets that store B needs. We'll send those from warehouse W. The problem is that only leaves 15 TV sets left for store A, and they need a total of 25. So the other 10 have to come from the warehouse in V, and it's very, very expensive to ship TVs from warehouse V to store A. So we have to kind of find a balance somewhere. All right, so before I go there, the answer to this question is going to come from, okay, how many TV sets are we going to send from V to B, from V to A, from W to B, and from W to A? So at first, it looks like I'm going to need 4 variables. However, the number of variables can be reduced by observing that what is not shipped from the warehouse in W must be shipped from the warehouse in V. So if we let X be the number of TVs shipped from the W warehouse to the store in A, and Y be the number of TVs shipped from W to B, then 30 minus X is going from V to A, because remember, store A needed a total of 30 TV sets. So X and 30 minus X, those two numbers are always going to add up to 30. And similarly, the number of TV sets going from V to B is 25 minus Y. Okay, so that way we only need 2 variables, and we can kind of proceed the way we did in the last, throughout this chapter. All right, so here's our diagram again, showing all of those variables. Okay, so now we'll go on and set up our constraints and our objective function. So the constraint for warehouse W is that X plus Y has to be less than or equal to 45. There are 45 TV sets in warehouse W, so they can't send more than that. And then in warehouse V, remember, this is the number of TV sets going to store A. This is the number going to store B. The total cannot be greater than 40, okay? And then we have several non-negative restrictions. So remember, there are 4 quantities here: the number of TV sets going from W to A, from W to B, from V to A, from V to B. All 4 of those quantities have to be greater than or equal to 0. So not only do we have our usual X is greater than or equal to 0 and Y is greater than or equal to 0, but we also have 30 minus X is greater than or equal to 0, and 25 minus Y is greater than or equal to 0. All right, so here are the inequalities. We have the X plus Y is less than or equal to 15. X plus Y is greater than or equal to 15. That comes from simplifying this inequality right here, okay? And then X is less than or equal to 30 and Y is less than or equal to 25. That is from simplifying 30 minus X is greater than or equal to 0, and 25 minus Y is greater than or equal to 0. And then we have X and Y are both greater than or equal to 0. All right, and we want to minimize the cost of transporting the TVs. So that cost is given by this expression: 3x plus 6y plus 5 times 30 minus x plus 9 times 25 minus y, which simplifies to this. All right, so now we will graph this system. So at this point, I have to assume that everybody is an expert at graphing these feasible sets. So I'm just going to show you the finished product here. Okay, so the feasible set, it's a little bit hard to see the way they drew it. So let me turn my pen on here. Okay, it's going to be the region inside this. I think it's a 6-sided shape, if I remember correctly. Okay. All right. So next thing we have to do is find the vertices, right? Oops, let me put my mouse back on. There we go. So they're just, okay, yeah, finding the vertices. All right, so as I click through this, you'll see they highlight the inequalities corresponding to the lines that are intersecting at that point. All right, so the intersection of these 2 lines is 0, 15. Of these 2 is 0, 25. We also have 20, 25, 30, 15, 30, 0, and 15, 0. So those are our 6 vertices. Okay, now I need to get rid of that. All right, so substituting each of those 6 vertices into the objective function, you see that the lowest cost is when x is 20 and y is 25, right? Yes. Total cost of 260. All right, so in other words, the most economical way to supply the TVs is to send 20 from W to B and for 25 from W to A, which means that V will send 10 TVs to store B and will send 0 to store A. Remember earlier we said that it's really expensive to ship them from V to A. So we're not going to ship any that way. We're going to ship all of store A's TVs from warehouse W and go from there. All right, so to summarize, sometimes it's necessary to use algebra to reduce the number of variables. Once the number of variables is reduced to 2, the steps for solving a linear programming problem are followed. That's going to do it for section 3.4, and that's going to do it for chapter 3. We'll see you next time.